So good morning, everyone. So today we have the special seminar that I guess no one has ever met Alex. So, I think everyone knows that Alex was a postdoc here, and unfortunately, he had to leave us, and now he went to the University of Balearic Islands, which I guess is a much better place to be. But so Alex will tell us about numerical hyperboloidal compactifications and waves in FLRW and neutron star and shell data. Go ahead. Thank you.
Thank you so much. I think you gave me the chance to again talk about my research here. This talk is actually split into two separate parts, so to say, for length approximately. The first one is going to be on some work I did with Flavio Rossetti, who's currently a postdoc in GSSI in Italy, but did his PhD here. And that consists of basically involving the wave equation on FLRW spacetimes with fixed background. And then I'm going to talk about some recent work I did on sorting spherical symmetric initial data for a neutron star, or at least including a neutron star, on a hyperboloidal slice as preparation for our future hyperboloidal work. So let me start with the first part. This is a bit of a motivation of why looking at this wave equation on convergent spacetimes, more specifically FLRW spacetime, that is, I will specifically give the form of the metric, but the idea is the usual metric with a scale factor that makes your spacetime, in this case, grow in a decelerated way. If we consider linear waves, they are the kind of object that allows us to model either electromagnetic or gravitational waves, which all travel at the speed of light. And if we now want to deal with the Einstein equations, they contain the key properties of the linearized Einstein equations. And these can also help us understand, for example, later asymptotics of solutions of the Einstein equations and understand the causal structure. And as I'm going to have a slice on the topic of the Huygens principle in the way that non-zero curvature can create scattering in the waves and how that interacts. And as I mentioned, this is joint point with Flavio. This is a prior work of Jose Natario and Flavio that appeared, and I think this is a motivation for the work. So in this case, we're considering the flat, so the FLRW spacetime with a flat spatial section vector, and here you have the scale factor in terms of what is called the conformal time, and the relation to the physical time t and the conformal time, and this is the behavior of let's say the decay of the field at late times, and for different matter configurations, the exponent may change. I'm going to be quick on this so I can focus more on the actual results we obtain. This serves as a motivation. And then we shall also consider hyperbolic case. And in this case, there were only rigorous proofs for some of the different scale factors corresponding to different spacetimes. And indeed, for example, the work we did allowed us to clarify some contradicting results in the literature, specifically for this decay here, where some prior works claimed that it used to be a -2, but from the numerical experiments we did that I will show, we obtained a -3/2, which also corresponded to what was found by Jose and Flavio in this work here. But let me tell you about the setup. So we're going to be solving the linear wave equation on the spacetime, and we will focus on seeing how it behaves at late times. So what is the decay of the largest amplitude of the field at late times? And we will do this numerically. We'll be able to see, can we recover the same results obtained using analytical methods. So these are the two types of spacetime we shall consider, and these are the corresponding metrics. As I mentioned, so this is the time, this is the scale factor, and this is the spatial part. And this is written in terms of the physical time, and this is written in terms of the conformal time. Conformal time is written to that one via A, the scale factor, in this way. This is for the flat case, where we just have an R square here, and for the hyperbolic case, where the sort of like more space in a way you can visualize. Here we have the singe of the radial line chord. And well, then the scale factor in the fact is given by the simple quality of physical time, but for numerical purposes, it was more convenient for us to actually use evolving conformal time, because for a shorter conformal time, we could reach a longer physical time, and that was actually more efficient and simpler. And in this case, this is the scale factor, and this one depends on a factor on some parameter p. And this p is going to be 0 for Minkowski, and we're going to consider up to the value of 1, almost 1. And then in the case of the hyperbolic case, this is the form that the scale factor has in terms of the conformal time, and different values of this parameter w will correspond to different cases. Yes, and in order to be able to evolve this, we consider some initial Gaussian-like pulse and just at the center, or we let that evolve with the neutron. And this is just some of what we found in this previous work that you cannot fully see because it's in the way. I'm gonna, that's it. So we basically performed the simulation the way I described, that was the setup, and these were the results we obtained, which are in accordance to what was found previously for the flat case. And in this plot, what you're seeing is the exponent of the decay, and that well, it covers the expected behavior. So for different values of p, we get different values of decay. So it's basically -1. What is this? -1. Yeah, I was told we need to finish it right on time, so I will not spend too long, but basically this is in accordance with what we expected. And before I show you the results for the hyperbolic case, let me say a few words about the Huygens principle, which means that the propagation of the information takes place on the surface of the sphere. Like if you have a torch and you light it, basically it's a sphere that is expanding. The same goes with the linear with the equation. And this Huygens principle actually holds in the flat case in Minkowski, p equals 0, and in the radiation case where p is 1/2. Now considering, of course, 4 space-time dimensions. So in this plot, you can see radial coordinate and conformal time. This will be our initial pulse, and as you can see, it propagates along the characteristic, and it's 0 before and it's 0 after. However, here for the dust case, where the Huygens principle does not hold, we see that initially it is 0 where the pulse has already fallen off, but at later times, there's like some tail decay that you don't see when the Huygens principle holds. So this is something that we could see numerically quite well. And just to finish on like these 5 results, which we perform in the usual way with the usual time and slices, Cauchy slices. We also obtain the results, expected values for the hyperbolic case. Again, you can see the exponent in terms of the logarithm of the physical, the pattern coordinate. And something that happens that in some of these simulations, we actually need to go to a late time to be able to actually see the copper decay. So when we're already in the tail regime, and that means that so now we hit some technical issues, which is our boundary conditions are not perfect. So it means that if the wave reaches the boundary, there's going to be some back reaction that should not be there. So it means for us, okay, if we want to evolve for longer, what do we do? Just make the domain longer. And then it's like we add more grid points so we don't lose resolution. But we also need to, so basically the point is that the simulation becomes more expensive because we need to create and evolve more data. And then we thought, okay, how about we consider the hyperboloidal approach that some of you may already have heard of, to be able to see, can this help in any way with this limitation we have that our simulation become more expensive? And now I'm going to show you how we basically recovered the previous results using this hyperboloidal approach. I will also like to tell you that while we managed to get it to work, it's not like all perfect. In some cases, the equations at some point may blow up. But I mean, we already managed to get the behavior we wanted. And in some cases, we recovered the solution. Sometimes things were not like super clean. So it's not perfect, but it did work. So something else happy about. And in case of someone who has not before heard about it, let me just give you a few insights of what is this hyperboloidal approach. So when we think about evolving a numerical spacetime in numerical relativity, this type of simulations, we basically give initial data and evolve it on time. And in order to give initial data, you have to need to choose some slice of your spacetime, in this case, one cost, which I'm plotting here on the left. And if you think about the usual time equals constant slices, you would obtain standard Cauchy slices, which are these solid lines here. Now, given that we have finite resources, we cannot evolve all the way to space like infinity, but normally what people do is you truncate along this dashed line and you basically what's inside. However, we are now dealing with problems that have some sort of fields that propagate at the speed of light. Fields that propagate at the speed of light, if you let them go far enough, they will actually reach functional infinity, which is not good. And following basically null slices. So this is actually our signals, the wave equation I was showing basically propagates on this type of slices. You were seeing the image about the highest principle. So this would work for the purpose of our simulations because we evolve on a fixed background. But if you want to actually evolve the Florentian equations, this approach, characteristic slices, may not be flexible enough because due to the strong field, if you have black holes, neutron stars, the generators of the characteristics may become tangent to each other, creating caustics, and that's something tricky to deal with numerically. I've never worked with it, that's my understanding. So something that people may try to do is to do, this is more for general relativity, it's also giving you the options here to see. So something which is called Cauchy characteristic matching or evolution basically uses Cauchy slices in the interior up to some voltage and then joins them two characteristic ones on the outside. So the information evolved can reach functional infinity in an ambiguous goal. And while this is indeed one way, and if you're into gravitational waves modeling and stuff, then you may know that CCE, Cauchy evolution, is the current method where people are having the same gravitational effect, which is one way of it's technically the only location in space that where you can extract gravitational wave radiation in an unambiguous way. Just to say that this certainly works, it has its advantages and disadvantages, and I'm going to advocate for another approach, which is the hyperboloidal slices. Sorry, that should just appear once. These hyperboloidal slices are space like everywhere so space like also the Cauchy slices are, and as such have similar flexibility to the Cauchy approach, but they are smooth, differently to that one. But the issue is that they are able to reach functional infinity without any type of approximations. And another nice thing is that as scribe classes are going on surface, all physical information is going to go out to the domain. So, like, we don't need physical boundary conditions because there's not going to be any back reaction from the outside, which is one of the advantages of having the boundary at functional. So let's try to see if we can use these type of slices to actually evolve our wave equation on for the FLRW spacetime of interest. So, and this is just for you to see like these effects I was talking about in the sense that, oh yeah, like, oops, sorry. So this is going to be a scalar field evolved on a Minkowski background, so p.0. And this is actually symmetric initial data. So one part of it is going to be to the domain. So scribe class is located at r+1, and the other bit is going to be reflected and then read. And the idea is that this corresponds to one of the slices that I'm showing. So it's going a bit slow. So this is part of the field. As you can see, it's leading to here. It's gone. The other one is being included at the boundary because of the type of initial data, and now it will be and in the end, nothing will be left. And the powerful part of this method is that, yeah, this is cry, everything is moved, but you don't need to do anything specific there. So this is the kind of setup that we want to consider now.
So Scry is at r=1.
Yes, thank you. Yeah. Scry would be exactly r=1. So you could set that to any other value. One is as good as any other. Right, so now if we want now to express our metric in terms of these hyperboloidal slices, check. Then the way you know how to do it is to consider the high function approach, where instead of evolving, so we express our conform, what I would call the physical conformal time, so this is the conformal time along Cauchy slices, that's going to be related to the conformal time along hyperboloidal slices, and this relation is given by the height function, which is basically what makes the slices go up. So you do that for the height function. So you do this height function, which is going to take the following form for each of the two options, flat and hyperbolic. As you can see, we're using the same functional form. When here this is the radial coordinate and with the radial-like coordinate. And then, so this is hyperboloidal slice, but this is still infinitely, it extends infinitely. So now we need to compactify it to be able to locate scry at r equals 1. And for that, we use this compactification. Now, this is different, given the different behavior of the radial-like coordinate in each case. And then we use this time-independent compactification factor. So this rho scry and r scry is set to 1. So that when rho or r are 1, basically that's scry. And I forgot to say this kappa is one parameter that controls the hyperboloidal slices, but it's not of much relevance. Now, this follows the approach that has been used from Minkowski in the past. There may be other options that work better. We try to look into maybe some time-dependent compactification, but it was not clear how to set the freedom we had. So for the moment, we stick with this on this first step, and then we will see what is done in the future. So with this setup, we transform our time coordinate, we transform our radial coordinate equations, which we then debunk. And if we then want to be able to actually recover the exponent for the decay, we still need to consider the decay on the original sort of Cauchy slices. So with the physical time, and this is the well, actually this is the setup that Flavio came up with. So our data is not going to be given on the red slices, but we will consider one of these green ones for a given time, and then we basically need to check where it interacts with the red slices and see where the maximum of the scalar field is given on that, and we will take that as our, let's say, as our decay for that T0, and then we will do that for different slices, and that will allow us to basically recover the same information we had before. So this is all the ingredients we need, and I'm just going to show some of the results because we basically recovered what we had before. This will be the case, the flat case for small values of P, and those are only going to behave like -1, and this is the recovered values with the left I just showed. And this was published in March, April this year, it appears, as part of this hyperboloidal collection. Right, so I mean, I have more plots. I'm not going to show all of them. Basically, things coincide to what we have here. To have, for example, hyperbolic case with large values of W, and they also coincide with what we expected in cases of -2 for the supremum norm of the scalar field amplitude. Right, and then something else that actually we include in the paper is we wanted to experiment with nonlinear wave equations. And the aim would be to study global existence solutions. And now let me tell you something about this, which is, so in terms of global existence, here, what I'm talking about is numerical simulations. Like we cannot really we cannot prove anything with numerical simulations. All we can say is that we set this problem up with this equation, and it ran in a stable and converging way up to this time. That's all we can say. Like, maybe if we run for longer, it will crash, do not know. And also, it can also happen that our code is crashing, but maybe that may not be related to the actual equations we are evolving. Maybe it crashes because of it's not properly implemented, if there's some mistake. So that is to say that whenever we have something which flows up, it will give us some insight. It will give us some intuition about how things may be going to the strict proofs, but we cannot really make any actual claims in that.
But why not?
Well,
I mean, in principle, you
You-
could say, so you discretize it in some way,
Mhm.
formulate it in matrices, and then you can show, okay, this particular algorithm converges, and then could even include some machine error and say, even this is machine error.
So no, this we can do, but I would say this is not as strong as when you look at one of the other paper when they do things like at the analytical level and say, okay, this has been, we have proof that this is, I know, small data global existence. Like here, we can just evolve out to some time. Like you cannot show it's gonna evolve forever, technically, because you cannot really evolve forever. I guess that's the point I'm trying to make.
But mathematically, you could prove that. I
Well,
mean,
but then you wouldn't do it numerically.
but you can prove it for the discretized system.
Okay, but the thing is, how much of that discretized system actually carries over to the continuum? I guess. Okay, it can be studied, but maybe you cannot make claims as strong as in the continuum case. Well, I mean, I'm also not an expert on this. I just wanted to make the point to say that okay, we're doing things numerically, we're not doing things continuously, because that's what I wanted to say. Okay, so that said, we looked at two different equations, namely the Fitz-Jones equation in this form. This equation is known for in Minkowski. So for p equals 0, for I forgot the technical word. Basically, there will always be an amplitude where it blows up. So the larger the amplitude, the earlier it will blow up. It will always blow up. So even if you have a very small amplitude, it will take a long time. At some point, it will become unstable. Then there is the null. So there's the null condition. Okay, that we generalized. In this case, there will be no scale factor. For the Minkowski case. Oh, and then sorry, just to mention this, we're considering the flat case, not the hyperbolic. So in the behavior of the null condition, generalized in this case with the scale factor, is that there is a small data global existence, which means that if the amplitude is small enough, then it will be valid forever. But for up to some large value, some given value of the amplitude, then there will be blow. My understanding. So there's a different behavior between the two type of equations, which are all of this form, which are not together. And now let me give you an example of how this looks. This is the flat case of equals 0.3. And what you're going to see here is a little movie. Here you're seeing actually the time derivative of the scalar. And you see many lines here, the different colors denote. So basically, it's the different initial amplitude they have. So look like the black one at the front, that is the last one, which has the largest amplitude. Then this yellow one has a small amplitude, small. And you will see how the larger the amplitude, the earlier it will blow up. Blow up in this case means that basically the values become very large. And let me play it and you'll see. It will be, yeah. So those blow up, then another one. As you can see, and the larger the initial amplitude, the earlier it was blown. So it's the expected behavior basically for the Fitz-Jones equation.
What's the meaning of the amplitude of time blow? Like, why is the blue line more than black line?
Oh, that's because so the code is about basically we're doing like finite time steps, and so that means that if you actually wanted to see the same, let's say, growth in the amplitude, that would correspond to not quite the same maybe interval of time. Like maybe if this instead of evaluating it at, I don't know, t equals 3.7, we would need to do a 3.726. But that data point in time is not available because we're just basically outputting maybe 0.8 by 0.1. So it's because of that. But if you look at the continuum behavior, you have all of the much more time resolution. You will be able to see them at the same.
So you're saying that the derivative is the same for the like.
So basically, this is stopping whenever the code has found that this has become either a non or a very large value, like overflowing, like it's e to the 300 or something like that, 10 to the 300, something like that. So it's basically giving you the value before it happens. And as this, like the output is discretized in time, that's why it doesn't look as big in all cases. But
why do the ones that crash later generally have a smaller amplitude? Is the time step bigger?
No, I think it's because they crash faster. So my guess, I have not looked into this for some time, but my guess is that the growth is bigger. So you would have, so between the time where it starts growing, you start to see that it grows, and the time where it actually crashes, it's a smaller interval as compared to. Sorry?
I still tried it and that time step, which depends on the amplitude of the so it tends to slide into the singularity.
Well, I mean, I think it would be simpler. That would be an option. I think it would be simpler to just maybe output more time steps to start with. But yes. In any case, it was just to show how what the I mean, give an impression of the blob within the direct in that particular. But yeah, so that's the way it looks. And also, there's something that actually I was a bit confused. I'm not sure I completely understand is for the two smallest cases, the blue one, another black one, which is actually behind all of these lines. The signal actually arrived at scry and there was no blow up, at least for the time that this evolution was run for. And I have the question, like, is it going to blow up afterwards, even if the main bulk of the signal is not there? That's my guess, but I mean, we did not run for long. So because this was enough for us to see that.
So can I ask, did you try compactifying in time? I know that there might be problems with that, but like
We
for
did
global
not.
existence, it's difficult even if it's numerically.
Mhm.
You know, global means also like in time, right?
Right.
So did you try?
We actually did not. We did not try time compactification, but that you mentioned it could be potentially useful in this kind of scenarios. So thank you for
Also because the pattern is fixed, right? So
Yeah.
also the
Yes,
pattern is
yes,
fixed,
yes, that's right.
but
That's right.
it's not as harmful as
Right, yeah. Yeah.
Yeah. But actually, so I mean, from when you even though they move all the way to I plus, I think they do resolution or something. But I think in principle, maybe not in practice, you could compactify that, right? I mean, letting alone the problem to make it.
So I guess it would require some more adaptations of the code, but in principle, it should be doable. Like if you can go compactify in space, you should be able to compactify that. So yeah. So yeah, that's just a visualization of how these things look. And then so the results we obtained between p equals 0 to 0.5 are actually summarized in this table, where you can see. So this is mean Cauchy. So for the null condition, we have small global existence dimension, and for the picture case, there's a blob at finite time, no matter what the amplitude. So again, later for small amplitudes and vice versa. And here, the way to read this table is that this value here is the maximum amplitude, or the way we are setting the initial data, for which we can run up to, I think it was t equals 10, we thought it was a late time because the signals were like being able to reach, to live through the outer boundary. And have three sets of convergence runs completed. So I mean, it was not blowing up. And this was the maximum amplitude where that was achieved. And now this delta P or blow up means that if we take this and increase it in this percentage, then we will get a blow up around this. So in the case of the null condition, this value is very small because up to some value of this A, so the amplitude, there is, it can run forever, there is no blow up, but so as a step function almost, then it's going to blow up. That's why this value is very small. And however, for the Fitch-John case, where we expect blow up, in any case, this was like a much larger value because that means that, okay, maybe we're not seeing blow up t equals 10, but we're going to see it maybe at t equals 30. So that's why this value is large. The interesting thing is, as you go for larger values of p, is that the delta stays very similar for the generalized null condition, but it becomes smaller for the Fitch-John case, which we interpret as a potentially changing the behavior and being a bit more like maybe there is something closer to the small data global existence behavior for the Fitch-John equation for this for an expanding space. And also you can visualize for the Fitch-John case the same thing I said before for p equals 0. There is a big change in like this is for this amplitude. So for this amplitude, it is getting to t equals 10. But for this amplitude, it's blowing up much earlier than this 2.8 I mentioned. But as you go to larger values of peak, for this amplitude, it gets to T+10, but it's only a bit bigger than that, then it blows up like this, will become more like the step that you see for the null condition. Yeah. So and this basically covers all of the work we did on this. Just as in the summary, just basically we use numerical methods to be able to sort of confirm experimentally previous results. Then we applied a basic hyperboloidal method to be able to recover the same results, and also used it to look at first glance at nonlinear equations. Extensions that we plan to do, we plan to study these more systematically, both on Cauchy slides and hyperboloidal ones. We may need to extend the treatment to something more sophisticated for the high function of the compactification, and we will also explore if we can use the hyperboloidal approach in other types of cosmological scenarios. So this is the first part. If there's any questions, maybe I can answer them now. Otherwise, I'll go to the next one.
Does the hyperboloidal method work better than the before?
That's a very good question. So I guess depends on what you want to do. So indeed, as I mentioned, we were able to certainly recover what we had before in a cheaper way, in the sense that we did not need as much resolution because we had a compactified domain, and we would have everything would happen also faster. We wouldn't have to wait for so long for the signals to propagate, for example. But as I mentioned, in some scenarios, I think, if I remember correctly, was the larger P, the earlier it would blow up, the simulation would blow up. That means if you still manage to see the decay, you would still get the information you wanted, but means you cannot really like move forever. So that's something we still, maybe changing this will help, but I mean, we still need to explore that.
I think whether we get what was the advantage of having a bended head function.
So I mean, I cannot tell you like specifically, but the way I see is that we're basically having a spacetime that is expanding. So if one way you sort of can, at the level of the equation, you can counteract the effect of that expansion with some compactification that takes that into account. For example, maybe this blow up I was describing to Jose now, maybe that doesn't happen, or so that would be the idea. That's the way I see it. I know it's not very specific, but that's what I was hoping. However, when you try to basically you try to feel the time dependence in H and the compactification, now there's a lot of freedom, and we find it hard to say, okay, how do we set it? So that's why we sort of as first step, basically do what we had done before and see that way. And while not perfectly, as I was describing, it allowed us to get what we had. Right, so I'll assume there's no more questions on this. You can still ask at the very end, something comes up. Then I will go on to the next part, which is going to be on the topic of initial data for hyperboloidal slices, including a neutron star. That's the main thing. And the work was motivated by this paper from Richard Stomgart and Shapiro, where they considered so the evolution of a neutron star with a small black hole at its center. That means that what will happen is that they use like as a spongy accretion. So that means that basically the black hole will start accreting the star and it eats up the whole thing. And we thought, well, I mean, this was suggested to me as a possibility to explore with hyperboloidal approach by Kotaro Kyutoku, who is a professor in Japan, where that was like suggested to me while I was visiting there in Kyoto in 2022. And so I said, oh, that's an interesting thing we could say. And then I realized I don't even have initial data to actually evolve this. So the first step, which is what I just put out on the archive a few weeks ago, was initial data that would be suitable for this type of simulations, but for hyperboloidal slides. And I'm going to be, okay, I will give some steps which may already be known to you if you solve the QV equations for neutron star type stars. Well, and something else I would like to motivate is that, well, you may know this person, Christian Peterson. So this is a plot we put in the spec from last year. And this is on the topic of hyperboloidal slices and how if you actually, to fully describe the system properly, they need to have information about the mass contained in the system in a way. So the blue slices are some hyperboloidal slices, and the red ones are another type of hyperboloidal slices. For at least that's the idea. But the dashed ones actually are taking into account the mass of this is for a Schwarzschild black hole, so they know about the mass of the black hole, and that's why these slices reach fictional infinity. Then, if you look at the solid ones actually would be similar to if you were compactifying Minkowski spacetime or equivalent. And these ones, they get to square paths, but actually they continually really join space like infinity. This is because those slices do not sort of know about the full spacetime, the fact that that spacetime includes mass and energy in a Hungarian way.
You know, like my understanding also of the question is that you don't need to know the mass very precisely in order to set up the slices, or
well, I mean, I did not check if you were just perturbing a little bit on the mass. Here it's either nothing or like the actual mass. I mean, maybe Christian, you have.
No, but I mean, this is not, say, real mass, but I mean, like, say, you recurrently say real mass, right? But it's analogous to constructing recurrent particles, right? We like to construct recurrent, or like for constructing recurrent coordinate, you need real mass.
Yeah.
but in full nominal evolution, like you know this something else.
So this, say, these like are filled with the TR part of the metric. So for that, you need to sort of have this analogous mass bits, right? And then the rest of, say, ADN mass needs to go on in the angular part of the metric, so that you can sorry?
Mass you know by
Yeah, so also they say the difference between, are you constructing initial data, which is what I'm going to be talking about, or is doing the evolution, maybe your black hole is accreting mass and then it grows. But if let's say the hyperboloidal slice is not something fixed, which for example in Christian's approach you achieve by using the equal evolution for that, then I mean then that will change, but that will change according to your mass. That's my understanding, right? Yeah, so but of this, like if you want to construct initial data and you have a neutron star, you have a black hole in the center, and you say, oh, I'm going to just use the height function that I talked about for Minkowski, that's not going to work. That was the basic technical message from the slides.
So when you say here these zero mass slices, they go to square plus. So they don't go actually to square
Not
plus.
really, not really. The thing is, Penrose levels can be misleading in some aspects because you compactifying a lot, so you don't actually see what is happening. And what does happen is that this one goes to scribe and stays. That one actually goes. This one stays and goes on the. So yeah, it's misleading, but the Penrose can be misleading. That's what's happening. Yeah. So okay, let me now move forward. Otherwise, we will be on time. This is okay, and I'm gonna go step by step on how you would construct initial data for a neutron star on for a spherically symmetric polytropic-like neutron star or a hyperboloidal slice. So, and we start with the usual data on a Cauchy slice. So this would be the ansatz for the metric for the neutron star. We have three parts that we solve using the theory equations. Here, E is the energy density. This would be the mass function for the neutron star. This would be this nu. This lambda actually integrates to this, and this would be the pressure. And now we relate. So I considered the simplest case I could think of, because the difficulty in this is not in let's say the construction of the neutron star, but in the hyperboloidalization. And as this will actually done numerically, you can use whatever equation of state you want. It should still work. So I consider polytropic-like equation of state where the mass is related to the energy density using this function, where this k is said to be 1 and this gamma is said to be 2. So if you solve this numerically, you will obtain this. This would be the energy density when it becomes 0. That corresponds to the surface of the star. And then you have the mass, which is 0 at the origin, and then basically it increases until it gets to the surface, and then of course the mass contained in this constant outside, it just behaves like Schwarzschild for this value of the mass. And I made also the comment about knowing the mass for a hyperboloidal slice is because, from my understanding, when you solve for the theory equations, you will only know the mass after you solve. Like you cannot construct the slices before you know the spacetime, which is not so. Which for black holes maybe. Anyway, okay. So you have the solution. This is numerically, and then you're going to say, okay, now I'm going to do the same, the equivalent height function change we did before. Now with there's no conformal terms here, so we use this relation, and you calculate the h, the height function. In this case, I am calculating h1, and the h prime by imposing that my hyperboloidal slice is going to be, it's going to have a constant mean curvature. No need to look into the details. Basically, this is the relation that you need to solve for h. This is something you integrate by assuming that k is constant, and then you solve this numerically. So you do the expression for your, that's also called the boost. That's what you need to actually to construct your metric on a hyperboloidal slice. And there's a lot of lines here. Let me tell you what this is. In black, you have the way this would look for a constant mean curvature hyperboloidal slice from Minkowski. If you were to have a black hole with the same mass of the neutron star, you would have this stuff going on. It diverges here. This is where the location of the horizon is because it's a horizon, so it's expected to be for the boost. And for the neutron star, that is the solid blue line, it behaves very similar to the black hole. At some point, it is different, and it goes to zero at the origin. So it's the Minkowski case because at the origin there's no singularity. There's no mass. Right, and here on this dashed line can barely be seen because it corresponds to the surface of the neutron star. And I'm just plotting here minus GTT multiplying the boost because this has to asymptote to 1 for a hyperboloidal slice. If it was going above 1, then something wrong was happening, but it's all fine. And now, if you want to plot this type of slices in a Penrose diagram, that's what you get. So the difference between both is the initial polytrop was not exactly the same, and also the choice of the constant mean curvature was not exactly the same, but they both correspond to different neutron star slides. So a foliation of the neutron star spacetime on a Penrose diagram, and this dashed line is the surface of the star. And this, as I mentioned before, this would these slices that we just constructed them are still infinitely long. If you want, you can compactify them. And using this, we're not familiar because I used the same expression before for the compactification. And so far, what I like to use to compactify is to impose that the initial metric be conformally flat. This is the solution has to be solved with the boost, with this metric function, with the mass, and the compactification. And this is what you would get in this scenario. So let me also explain all the different lines. If you do that for Minkowski, you will get the black line. And this compactification goes to 0 at r equals 1, which corresponds to scry, because it's compactifying the infinitely long slice on that side. If you were to consider a black hole with the same mass of the neutron star, you would get the dashed line. And in this case, the compactification factor also becomes 0 at the origin, because this slice is a trumpet slice. It is also infinitely long inside of the horizon, because it sort of it gets to an innermost value, the Schwarzschild radial coordinate, but then the proper length is actually infinite. So that's what we are compactifying here. So this will be the location of the trumpet. This is scribe, and now for the neutron star, which is the one we're actually interested in, you get the solid line and something in between both. So they all behave the same as scribe, and here it gets to some value which is smaller than for Minkowski because of the presence of the mass of the neutron star. And again, and this is the location of the neutron star surface. And for the black hole case, which is a separate case, this will correspond to the location of its horizon. But actually, they're two different spacetimes. So I'm just putting them together to compare the compactification. Okay, that was the simple part. Now let's go. Okay, we want to have data with the neutron star and the small black hole in the center. How is it going to be? So, and I spent, this was on standby on my head for a long time, actually, figuring out how to do these things with the hyperboloidal perspective in mind. So the first part will be just this, so the theory equations for a neutron star. Then the point is we want to express it in isotropic form to put it together with a black hole. So you can either solve it as I described, or you can solve it directly in isotropic form. And then you can add the conformal factors. I'm going to explain it in more detail. Of neutron star black hole, so basically you're having a space-time that includes both. Now that is not going to satisfy the constraint equations by default. So you will have to solve at least the Hamiltonian one. The other one, is straightforward. And then once you have the constraint-satisfying space that includes both neutron star and black hole at the center, then you do have polarization. You can compactify to obtain data that you can use them both. So now, in terms of expressing things as the isotropic radius, this is the way we want the metric to look like. So that this will be the conformal factor expressed in this form. And this R bar is the isotropic radial coordinate. So this we can calculate for the solution we found at the beginning, but it's all used numerically. For the black hole, normally this would be 1 plus mass over 2R. Here we're not considering the 1 because the 1 sort of is already included in the neutron star part, so to say, the one that is if we want to shrink off the space time. And so we put those together, and then we include the yet unknown correction that we solve the Hamiltonian constraint. So this is the you want to visualize how this addition looks. So 1 is again just Minkowski. If you just had a black hole, so chi, actually forgot to mention this. This chi is, you can also call it a conformal factor. Is sign for the ones. I just plot chi because I think it's more visually, because chi blows up, well, sorry, psi blows up at the origin, while chi does not in the black hole case. Just have a black hole, so the blue dashed line. If you have only the neutron star is the solid blue line, and if you put both together without taking into account the correction due to the constraint solving, it would look like the dashed black line. So here it's including both objects, that's why it's modiform, so to say, and it goes to 0 because there's a black hole at the origin. Okay, so then we set up, this follows exactly, this is not yet hyperboloid, this is just follows exactly what was done in this paper, where this is the equation you solve for psi, where psi again is going to be the addition of all of the 3 contributions. Then you can conformally rescale ADM density, this rho, and you have this freedom, which is very useful because the psi is going to diverge at the origin to the difference of the black hole. And if you choose m in a clever way, so for m equals -6, then you don't have that blow up and you can solve. I actually understood that it took me many attempts and I was not getting anywhere until I did it. So, and these are the conditions. So this is the Hamiltonian constraint satisfied only for the neutron star. This is the Hamiltonian constraint satisfied only for the black hole. And if you put everything together, then you obtain the Hamiltonian constraint in terms of the correction delta phi in terms of the quantity, and this is the actual equation you solve for. And as outside of the neutron star surface, you expect your space-time to behave like a Schwarzschild black hole, you will assume, which basically behaves like this form. That's the sort of like the assumption you make at the surface, and you solve the inside. And you also obtain the value of this decay. Yes.
So the most conventional value we should be -8, I think, in this case. So if you go over -6, do you see that problem again, or is it something that you have to?
So if you use something which is bigger, bigger in terms of like less negative than -6 or -5, I think that because you have this factor. So if you don't counteract this, then this is going to be off. That's why they're using the -6. I was not actually aware that the common choice is -8. So thank you for that information. But if you try something like -4, then you will still have the problem.
Right, but so all the way to like -5, this is usually also motivated by existence and uniqueness of the solution. But usually anything over that, like in absolute value, would be good enough. But I'm wondering in this case, like if you have -7 or -8 or whatever.
I did not try. I expect that would also work.
Oh,
So, but again, I did not try. That's my guess. But I see no reason why it wouldn't. It would solve it.
You have all powers, so n is an odd number.
Uh-huh.
I would suppose you have for because of the behavior of the John equation or the British equation, for example.
Okay.
Powers for it.
Okay, I was not aware of that possibility, so I just took the value that was given, but that's interesting to know. Okay. Yeah, so that's what we're solving. And well, just okay, convergence. Okay, for this convergence test, I have to say, like, this was based on prior solutions that I obtained with Mathematica. So even if I did obtain rather nice convergence for the solution, and then so between 0 and almost 0.4, which is the location of the star surface. And I'm solving from here to there. So it converges nicely, but again, there may be other small errors that are not taken into account. But that was just a check that everything was fine with the solving procedure of the Hamiltonian constraint. And if now you want to look at the solutions, and these are small, so in principle, so I'm just choosing small values of the mass of the black hole. The mass of the neutron star is considered at least an order of magnitude. And I was choosing small values because that was the standard that was considered in the paper by Richards from that I mentioned. If you actually look at the solution, it looks something like this. This looks a bit strange because I'm using logarithmic plot on both sides and I'm putting the minus, so it looks nice. But indeed, what you see is that the smaller the plus hole, of course, the smaller the value of the correction, and closer to that's what is being shown here. And this is okay. On the left here, you have a plot from the paper, and on the right, I made the equivalent plot from my setup with the same values of the mass I just showed for the ADM row, also similar quantity in some scale, and just to show you, yeah, it corresponds to the same setup. And the smaller the value of the black hole mass, like for even close to the origin, this quantity is not zero. But there's just as a check. And so generally, though, I will consider a bigger mass of the black hole so that its effects are bigger, just for the challenge of making sure that the construction is done properly. And now, okay, now we want to hyperboloidalize this. But in order to hyperboloidalize it, we need to express it in terms of an areal radius, like in this case, not in the isotropic case. So for that, actually, we have to undo the transformation to isotropic coordinates back to the areal type ones, because we want to do the compactification in the way I described before. And that was a tricky thing, because if you have a black hole, the RR component of the metric actually changes sign. And if you just try to naively go from here to here, that is not well taken into account. Like it was tricky. I'm not sure the solution I found to this was the optimal one, but it worked. And just to illustrate this, is that this is the relation for a Schwarzschild black hole mass 1 between the areal type or Schwarzschild radius and the isotropic radius. And if you plot this one in terms of the Schwarzschild one, you get this solid line here. But that solid line actually, it only covers the outside space from here. I'm saying m equals 1 is the Schwarzschild radius to m. So this is only what you covered in the real solutions to this equation. But I also needed the information from inside of the horizon, because I'm interested in creating trumpet slides that indeed do reach inside of the horizon. So, and if you look at solutions to this equation, so the isotropic one in terms of the structural one, you see there's the complex here, the solution is complex, the way this is set, and it actually has this form. So, say it in brief words, what I did was an equivalent version to this solution for the numerical construction of neutron star plus black hole in the center, to be able to go back and obtain the RR component of the metric that was suitable for the hyperboloidal. And here I'm showing 1 over GRR, close up, 1 for Minkowski. If you just consider the neutron star, it asymptotes to 1. This is in log scale. It's some smaller value because of the effect of the mass around the neutron star radius, and then it goes back to 1 as you go towards the origin. And if you consider now the neutron star plus black hole plus the correction, it will look something very close to the neutron star, but then it will deviate and behave like a black hole solution does as you go towards the origin. This is actually a solution for a small black hole mass. And if you want to compare it to a bigger black hole mass, here you see that indeed this line here corresponds to the location of the horizon for that space-time, and it's farther outside because the black hole is bigger as compared to this one, the black hole. So this is the 1 minute. Okay, right. All right, so that's a construction. Then I set this choice for the time component, and using this you can calculate the boost, and you need to choose a specific value of PCMC so that you obtain a trumpet, otherwise this slice would not be a trumpet, and this is what you get. So this is the hyperboloidalized version of the neutron star black hole plus correction. This is a trumpet geometry. This is just numerical with the interest of getting close to the horizon. And you may see that there's this dashed line here. That actually corresponds to the location of the surface of the star. So everything you see is inside of the neutron star. And that's just an effect of the compactification. I tried to change that, but it was not easy to visualize, so I just kept it that way. And if you then do the compactification the same way I described before, you will obtain that for the dashed black line corresponds to the addition of the 2 objects plus correction. And it's qualitatively the same as the black hole, but it's changed because of different mass content. This is ready for numeric. This can be used for an evolution if we want to. The only thing is that is not yet set. I need to basically work on now into the relativistic Cauchy equations to be able to evolve this type of initial data within the hyperboloidal approach, which has not been agreed. That's the next step. And yeah, the idea would to evolve a neutron star, then a perturbed one, and then consider this one the accretion scenario that I was talking about at the beginning of this part. Yeah, so, and okay, this was, okay, I'm gonna very quickly dash through. This was just the motivation to why null infinity is important, especially when we want to perform numerical relativity simulations that aim to create waveforms, and they can only be unambiguously measured at square plus. And so you may have heard about the Great Hyperboloidal Research Network, of which some members here you may know. So we do seminars and everything, newsletter, like and subscribe, please. And we're going to be organizing a workshop between the 16th of January at the Erwin Schroeter Institute in Vienna. If this is something you are interested in, have a look. There's not a lot of space for participants, but we will consider interested people, of course. And that's all. Thank you for your attention.
Check if someone is ready because we still have to. Yes.
I mean, we can leave it all.
Time for questions.
Okay, so then please, if you have any questions, feel free to ask. I will leave the advertising here.
So going back to the first half.
Yes.
Did you do the Fritz-John vision previous method?
Not yet. We actually did not. We did not do Fritz-John with the Cauchy evolution. Not yet. But that is something we want to compare with, indeed, to make sure that there's nothing went wrong with doing the hyperboloidal approach. And as I mentioned, I was very interested to see what would happen indeed with these simulations where the bulk of the signal actually lived prescribed and it had not blown up yet. and you expect it to blow up. So that's something I would really like to understand.
And also, you don't have yet any exact results, like mathematical results to compare.
No, not that I know of. No. So, oh my God, yes.
In your motivation, you said you want to, from these tails, you want to say something about cosmic censorship, right?
Oh, okay. I put it as potential motivation also. We were not addressing that question specifically.
Have you done anything on the evolution of the neutron flare?
Not yet. That will be the next step. So once I'm back in September after work conferences and stuff, I plan to sit down and see how that can be done. So again, the step will be first consider just the neutron star, see if that can evolve and basically behave as expected. Then perturb it, maybe with some radial perturbation, maybe throwing something in with scalar field. And then they would then consider just plug in the black hole plus neutron star initial data and see what happens.
How much do you know? How much work has already been done with hyperboloidal slices in massive fields?
That's a very good question because by default, so there is prior work of David, me, and a postdoc currently in China that dealt with solving the massive wave equation. So considering several types of wave equations, including the massive one. And for the massive case, that did not work properly in the sense that we would not get it to converge at fictional infinity. And what was happening, if I remember correctly, was that from the physical perspective, like you cannot expect a massive quantity to arrive at star because it will not follow larger distance. So that's a bit of a, if you consider boson stars, because the scalar field propagates at the speed of light, but if it's massive, that's a bit of a strange type of object. So going back to that, what was happening was that high frequency oscillations were excited very close to scribe. And the thing is, hyperboloidal slices, outgoing ones, like the ones I'm describing, are meant to track outgoing radiation, but they're not good at tracking ingoing radiation, especially if we're close to fictional infinity. That gets under result. Like, it doesn't work well. So I guess that goes at the base of the loss of resolution. Like I have talked with other people, and people are like, oh, but maybe we can get it to work, or maybe there's other options. So I'm not sure if the topic is completely closed, but that's something which is not straightforward. And again, like I was having interest in actually being able to maybe consider like a boson star or hyperboloidal slices. My question is, can we have a massive term that is not constant everywhere, maybe falls off at infinity? And that maybe that works. But again, something I really wanted to try for over a year. That's
Like it seems that the hyperboloidal slices are especially well adapted to things that move at the speed of light.
Yes, that's right.
You have a massive field and it's going out, like see some accumulation in your.
Yes. That's right. And that's something very interesting because what I would like to also see is to try this guy, like this type of initial data, and see what if there's like mass being ejected from the neutron star, whatever is happening, how is that going to behave as it propagates outwards? Because indeed, at some point it will start to be slowed down, it will be unresolved. And that was a good question to see how can we deal with just the vacuum part, which travels at the speed of light and everything is good, with having mass which will not travel at the same speed and cannot get that far. That's something I'm very curious to be able to try it, which was also one of the motivations for doing this, like this initial data that can be suitable for this type of tests.
So I'm not so convinced by this vanishing mass term, or I mean, you said
you mean this?
Like you said in your boson star.
Oh, right, sorry.
Consider a mass term that goes to zero.
That's cool.
So of course, I mean, there's this constant mass term, maybe if you.
Yeah.
But physically, I think it would make sense that particles become lighter or become vanishing, have a vanishing mass, not infinity.
Well, so the thing is, so the way I'm visualizing things, like you expect to have your boson star big, that's going to be okay. Let's put it at the center of our domain. So there, the mass there's going to be a massive term, which is going to be constant for as long as that, until the surface of that star. Thing is, far away as we go to infinity, will it affect if then the field goes down and basically disappears at scribe?
Yeah, so I mean, if the field goes down, okay, then of course all terms go to zero, right? But the mass,
So the
the
thing,
mass factor must stay the same.
right, but the thing is, if the field goes to zero, will it see that the mass is also going to zero farther out? I haven't tried. I'm very interested to try, just I haven't found the time. Because if it works, or if there's a way to make this work, that would mean you could also do like consider boson stars in the setup. Yeah, something to try.
If you enjoyed the video, like and subscribe.